analyzing and testing group. And this is sort of what I look like at the moment. I've been in rheology for well over 25 years, studied chemistry and environmental science, worked with 2 other rheology companies, and joined Netch 2.5 years ago when they purchased the rheology business from my previous company, Malvern Panalytical. So here we are. My colleague Vivek Shahi should be in the audience there. So if there's anything that I miss or any questions that we don't have time to answer, you can certainly discuss that with Vivek. What I would like to do at this time is to just do a quick survey and see how many people are currently using rheometers or viscometers or have some background in rheology. I can't see your hands, but if I can get some idea of how many people have some prior experience in rheology, that would be helpful. No? Any show of hands? Right, no answer. So what I will do then is just continue on, and of course, the subject matter is going to be rheology, specifically in pharmaceutical applications. And a lot of the information in rheology in pharmaceutical applications are proprietary. So, the companies who are doing the work will not always publish, their work. So a lot of what we do under a secrecy agreement or a non-disclosure agreement. So we can't, share that with the public either. So what the focus will be on is basically how to use the rheometer, to help characterize, different materials under different conditions. It could be pharmaceuticals. It could be in R&D or formulation development, or in some cases in quality control of the final product. But I certainly hope you leave this presentation with some idea of, or should I say, a better feel for how rheology can be used in the pharmaceutical industry. So whether or not you had some prior experience with rheology, in your work or in your studies, the reality is that you must have had some experience with rheology even this morning. If you took a shower, you used maybe a soap or a shower gel or a shampoo. If you use a hand cream or a hand lotion, or some hair products, those products are also developed and formulated using rheology at some stage of the product development. Toothpaste, for example, and so on. All right, so let's move along. This might last for about an hour or so, maybe just over an hour. So we'll have questions and answers at the end. And hopefully we'll, all leave here with a better experience. Right. So, like I said, I work for Netch Instruments, and the group that I work for is analyzing and testing. That's the business unit, and We manufacture and supply instrumentation in thermal analysis, on the Rheometers, of course, and some other instruments that you look at thermophysical properties like thermal conductivity and diffusivity and so on, dilatometry. There are two other business units under niche. One's grinding and dispersing, and they make devices for grinding, dry grinding powder mixes, or liquid, or dispersing, or homogenizing. And of course, that's done in a wide range of industries: pharmaceutical, food industry, energy storage, personal care products, and so on. And then the other group is pumps and systems, and this is where they in manufacturing, very precision-made pumps are used to deliver products on a very precise, very controlled conditions. In the analyzing and testing group, there are two components to this. We of course sell instruments, but there's also a testing service that we offer, a paid testing service. And in both cases, our goal really is to improve the understanding of materials. So we try to broaden the understanding of materials using both techniques, thermal analysis and rheology. Niche itself, at least the analyzing and testing business, is global. So if your company has facilities in other countries, we can support instrumentation or service and support across a wide range of geographic locations. There are about 500 employees worldwide under niche analyzing and testing. Some production facilities in Asia, of course, in Germany, several laboratories, and just a number of sales and service locations in South America, Mexico, of course, North America, Asia, and throughout Europe. Okay, so rheology. This is known as the study of flow and deformation of matter, and is used very widely throughout a number of industries. Of course, your particular interest is in pharmaceutical and probably personal care products, but the food industry, ceramics, petrochemicals, of course, plastics and polymers are a very big market. Paints, inks and coatings, adhesives, asphalt, batteries, components. These are all industries where rheology has almost become routine. So what exactly does the study of flow and deformation means? If we go back a few years ago, well, more than a few years ago, perhaps, let me just back up for a second. The first, one of the first recorded evidence of rheology, being taken seriously, occurred in the mid-1800s when two scientists, Hagen in Germany and Poisson in France, attempted to measure the viscosity of water. And on the right-hand side, you'll see a sort of primitive-looking device that was used, using capillary tube and a floater that was used to capture the pressure and try to develop some quantitative measure of the flow properties of water. This has advanced quite a bit throughout the years, and presently there are several types of rheometers. Commonly rotational or dynamic rheometer, capillary rheometer, and more recently there are microfluidic systems where you can almost have a viscometer on a chip So the rheometry part of it, the instrumentation part of it, has progressed quite significantly. For the pharmaceutical industry, I'd say the technique that's most common is the rotational or the dynamic technique, where you have a cup and a bob system, or concentric cylinders, annular systems, or parallel plate systems where the sample is captured between two plates, and in some cases also a capillary system where the flow through a tube, or capillary, is the technique that's used to make the measurement. So if we say we're going to focus on the rotational or the dynamic rheometer, keep in mind that there are two components to this, and there are two sections, fairly distinct sections, that you should become familiar with. One is what most people are familiar with, viscosity, all right, which is the measure of resistance to be made to flow. And if you've heard of viscometers, this is principally what viscometers do. They measure the flow properties of a sample. We'll get into that in a bit. So under the flow properties, or viscosity, of course, and there are a couple other types of experiments that can be performed, yield stress, and some other thixotropic experiment. We'll get back to that. And also, very important, perhaps not as well known or understood as viscosity, is the viscoelastic or viscoelasticity, or the deformation. So a few slides back, I said rheology is the study of deformation and flow. Right? The deformation component of it is shown in the viscoelastic properties. And this is really how the sample behaves before it's made to flow. So I could give you a soft solid or a liquid, and I can tell you by using some technique that's going to give me the viscoelastic information, quite a bit about the sample before we even attempt to start to measure the viscosity. So with this, you can predict a fair amount of sample properties. The experiments common are an oscillation type experiment, derivative of that are creep and relaxation experiments. So we'll just quickly take a deeper look at these two components. There's also a third one which I should mention here, which is there's also the axial geometry, where instead of flow or the classic deformation, we're measuring the sample using axial forces. And in this case, you can measure the forces, say, that's required for an adhesion or cohesion component, or just tack properties. So, for example, if you had a medicinal patch, you could really measure how much of it, how it's going to stick onto your skin, what sort of forces are required to peel it off, and so on, using the same rheometer. Right. So viscosity, then, let's look at the viscosity or the viscometry portion of the or the flow portion of the the rheological divide. Viscosity is, of course, the resistance to flow. And we typically measure or we apply some sort of force to that and measure the response. And we typically will increase the force or measure or apply a force over a certain range and measure the response. And those two components, the applied force and the response, we can use those two components to get the a viscosity, an engineering measure of the viscosity. We can do this either by applying a shear rate and measure the resulting stress, or applying a stress and measure the resulting shear rate. So we need to get familiar with these two terms. Excuse me. So the stress we're going to apply, and we use the rheometer to apply the stress to the sample. And the stress is calculated based on the force that's applied and the area over which it's applied. And we measure the resulting displacement as a result of the stress that's applied, and that gives us the strain. And if we can measure the displacement per unit of time, that gives us a more pragmatic unit, which is the shear rate that you'll be hearing quite a lot about as we go forward. So these components, the ratio of these two will give us the viscosity. And there are just numerous ways of getting this. But again, in the pharmaceutical world, the rotational rheometer is the instrument of choice in just about all cases. Just again, to more clearly define these terms that you'll keep hearing. Let's say, for example, we're taking this technique where we have a cylinder in a cup, and the sample is between the outer diameter of the cup, of the bob or the cylinder, and the inner wall of the cup. So we've got a defined area, right? And let's say we take just a small component of a sample that's in this annulus, and we apply a stress. Apply a force really over a certain area, that computes to a stress, and we measure the distance over which that portion of the sample has moved. So we now have a new value, which is the distance. We already know the gap between the two boundaries, as it were. So from that we can get the strain. All right, and we're talking about distance. Deformation is moved some distance, whether it's in meters or centimeters, and the gap would also be a similar distance measurement. So there really is no units there. They cancel each other out. And if we go beyond that, we'll see that the shear rate, again, is a measure of the deformation or the distance the sample has moved over the gap, another distance. But in this case, we're talking per unit of time. All right, so the two distances cancel, and we're left with a reciprocal second. So we constantly refer to shear rates with a unit of reciprocal second. And this technique, or you can very clearly define the shear rates in most processes, because you're either pumping things or mixing things. And once you have these two components, or in this case, three components, you can get a very precise idea of a shear rate. Okay, so why is that important? Because again, if you're going to use a rheometer to try and mimic any sort of a process, of course, the temperature might be important, the pressures might be important, but again, in terms of a deformation or mix in the sample or stirring the sample, the shear rate is what's going to normalize across, a very wide range of processes. So if you take it, then the rheometer has, well, the rotational rheometer certainly has a very wide range, maybe up to about 10 decades of shear, realistically from about 10 to the minus 5 to about 10 to the 5 inverse seconds. So that's a pretty wide range. So, you can set up experiments to mimic what happens in a storage condition where, the stresses are, largely gravitational. So the sample sits in a container and, it's just, acting under gravity. Or you can move along to higher shear processes, dipping, pouring, mixing, pumping, spraying, could be injecting also. And the idea then is you wanna, if your process is in in one of these areas, and you want to test your sample to see how it behaves under similar conditions, your goal really should be to try to do the testing under conditions that are similar. So a combination of temperature, pressure, and shear. So there are different types of rheometers that will perform better in different ranges. The rotational is certainly the one that I'd say captures the widest range. There's also a capillary rheometer, one made by Niche, that can get you to very, very high shear rates. So if you, for example, wanted to capture a material's behavior under very high spray conditions, say crop spraying, crop dusting, you probably would use a capillary rheometer to get to study how the material behaves when it's subjected to those kind of shear rates. The viscometer that some people or a lot of people use, again, viscometers are generally more basic instruments, and you can see that they cover a more narrow range of materials or narrow range of shear rate. So one of the things to consider then is that for any given process, for any given materials, the material actually is subjected to, excuse me, quite a range of shear conditions. And excuse me, so let's start with storage. The material, the product is made, and it has to be stored at some point. All right. So what is the viscosity going to be while it's stored? Is that going to change? Beyond that, I'm not quite sure why it's moving. Beyond that, in terms of how the sample is being used, right, that takes into account also what the user experience is going to be. So, the user has to, somehow get the product from the packaging, so it can be used. Sample application. Okay, for example, let's take the example here is could be a lotion, let's say. So it's in storage. The material is fairly high viscosity. It's at rest in a container. The consumer now gets the product, and the consumer starts to use the product, and here the viscosity is going to change because again the consumer is going to apply some sort of shear in using the product. In this case, the application, for example, to the skin. So it's been applied to the skin, and then the consumer or the user starts to rub it into the skin, which is a higher shear process. So the viscosity in this case is probably going to decrease. And so all these different components have to be taken into account when a product is made. You certainly wouldn't want the consumer to have the product at the same viscosity as it was in storage, because then it would the feel of it on your skin or just being able to use it would be very difficult. So the material has to be characterized, or the viscosity measured and controlled throughout the entire life cycle of the product, so to speak, from storage to end use. Now different materials will behave differently when tested, and these are some examples of very well known and very studied types of behavior. So, for example, if you were to measure the viscosity, run a flow curve on water or very low viscosity solutions, you'll see that the the stress will be the ratio of stress to strain will be fairly constant. So the slope on this will be constant. So you end up with a Newtonian materials where the viscosity, if you plot viscosity against shear rate, the viscosity is going to be constant. You have a class of materials that are shear thinning, so the viscosity decrease as you increase the shear, which was the case in the example I just showed on the lotion. And there's a third, perhaps not as commonly experienced set of products where the viscosity will increase with the increase in shear. And obviously, you need to be well aware of this, if this is the case with your formulation that you're working with. All right, so should I get a viscometer or a rheometer? Viscometers are certainly more popular. They cost less, they're more simple, easy to operate. In some cases, you don't need a computer. There's a LED readout that will give you a number. However, the materials that you can test with these are fairly limited. These are just some basic examples of viscometers. And, they seem to work okay with Newtonian materials that aren't going to exhibit any sort of strange or, unpredictable flow behavior. So for the most part, the viscometry will give you viscosity only. You won't get the viscoelastic properties or the axial properties that I pointed out earlier. In most cases, the measurement is relative. So you can't go necessarily from one viscometer to the next. The results might be different because again, the system is not very clearly defined, and you can't be it's not an absolute measurement. It's more a relative measurement. The range is very limited, typically. Temperature range is very limited, and it doesn't have the sensitivity that you need, for example, to test, low viscosity materials, protein solutions or materials like that. So, these types of instruments, they do have a place because, again, you can get a quick measure of, the viscosity, as it were, albeit a relative one. But this is definitely not the tool that you would want to use to develop sophisticated formulations, in pharmaceutical. So this is a rheometer. This is niche rheometer, the Connexus, and this has some, very, very clear advantages. Very wide temperature range. The gap that I spoke about between, parallel plates, for example, would be extremely accurate and very well defined. The motor system sits on the measurement tool sits on an air bearing that's very sensitive, frictionless almost. So any sort of material response you get, after you apply a stress is, a function of the material being tested, not, the mechanics of the system. Of course, very sophisticated software that, controls, the measurement and analyze the data. So again, this is a device that's, multiple times more versatile and more applicable to pharmaceutical situations where you're working with, APIs that are very pricey or excipients, that can be very sensitive. How does this thing work? It has a motor that, that's used to apply, the torque from which, the stress is calculated. And this, the entire thing sits on an air bearing here. Below that is a position sensor that tells you where or how much movement, the measuring tool has undergone. And from this, you can measure either by controlling the applying a stress and measuring, the movement as a result, or you can apply a movement or a rate and measure the stress that results from that. So we say it's, it can be controlled stress, so you can control the stress that's applied, or it can be controlled rate. So you can control the rate and measure the stress that results from that. And the decision to go with either technique, might be related to a particular process, or might be related to, the application of the material that's being tested. These are just some other features of the instrument. So of course you need an upper measuring system, a plate in this case, and a lower plate. So hence the term parallel plates. And your sample sits between these, and usually it's a very small gap. This has just been, exploded to, for illustration purposes. You want to be able to measure the gap precisely to, microns. And you are also able to measure, the force from the sample up against, the plate, which is, the normal force, which again can also be a component of different materials. And of course, the system can be temperature controlled, typically from about -40 up to 300, over 300 degrees Celsius. And as far as the type of measuring system that you can use, these are the three common ones that are used on most rheometers, whether it's net rheometers or company XYZ rheometer. You can have a cone, small angled upper. So this somewhat similar to having a plate, but again, this is a cone, and the reason for that is that this arrangement gives you a constant shear rate. If you notice that, the velocity is going to be different from the outer edge to the inner edge, and and of course the gap as a result. So it's very specific, very well defined, to give you constant shear across this entire sample. And these are typically anywhere from 10 millimeters in diameter up to 60 millimeters in diameter. So this is one a very common tool that's used. Of course, the upper cone in this case is affixed, to the chuck of the rheometer. The lower plate is passive, so the sample sits on the lower plate, and you lower the upper plate to make contact with the sample. And the entire thing is, temperature controlled. Then there's also, of course, more common, or just as common, is a plate and plate, or a parallel plate arrangement. The sample sits between the two plates. The upper plate is made to rotate or oscillate, and we'll get into that. Again, the lower plate is passive, just temperature controlled. And then there's a third system, the cup and bob, where the bob, or the upper cylinder, is affixed, to the rheometer. You have a lower cup, and the sample, is contained, between the walls of the cup and the bob. This is used primarily when there's in two instances. When you have a sample that is extremely low in viscosity, although you can also use, the parallel plate system for low viscosity materials. But if there's a chance that your sample is going to separate or settle, you're better off using a cup and bob arrangement, where the rotation of the bob, will keep the sample, from settling. Big difference also then is that this requires a much larger sample volume. So if you have a very small sample, a protein sample, for example, your choice would not be a cup and bob, but would be either of these two systems. One drawback of the cone and plate system is that if you have a sample with particles, you certainly want to be aware of, the very small gap at the apex of the cone. So your particle needs to be at least a tenth of the gap distance under the apex of the cone for you to have some kind of confidence in being able to get reproducible results. The second part of the rheology that we're discussing is what's referred to as the oscillation. And in this case, instead of the upper system rotating, it oscillates back and forth, applying a sinusoidal signal, very small angles typically. And from this, we can get, again, a lot of information on the material before it reaches the point where it starts to flow. This is a sort of a non-destructive test. So you would typically perform this test before you go to look at the viscosity of the sample, which is a more destructive test, because with looking at the viscosity, you're typically applying, higher shear, and that's going to break down the structure of the sample. With this, you can probe the sample without destroying the structure. And from that probe, you can get, a number of, you can realize a number of properties of the material, that can be quite useful. So with this, then, what's important is that from the oscillation, you can get, the modulus. So we can measure the stiffness of the sample. Essentially, the higher the modulus, of course, the tougher the sample. And what's important is you typically perform a test by applying an input stress, let's say, again, back and forth, and measure the resulting strain. Or you could do the inverse of that. But either way, you need, again, these two components that we discussed earlier, shear stress and a shear strain. Notice that, in this case, we're talking about the strain rather than the shear rate. And that gives us the modulus, or the stiffness of the sample. So I'm going to throw in another phrase, which is the phase angle. And this describes whether a sample, how elastic or solid-like, or viscous liquid-like, the sample is. And most material will have some combination of the two. So for sample that's purely elastic, we say it's, it's in phase. So the phase angle, there's no phase drift. So the phase angle is 0. I apply a strain and get an immediate, result in stress. Whereas for material that's more liquid-like, the stress and the strain are out of phase. And for something that's, that's purely viscous, it's going to be 90 degrees out of phase, as you can see here. So most materials are somewhere in between these two, between 0 and 90. And when you do an oscillation test, the result, typically, you're applying some sort of, an amplitude at a fixed frequency to identify where you can perform the test. But in most cases, the material will show you, or the test will show you where in the range of these two boundaries, the sample falls. And that's usually a unique feature, a unique property of the sample, like referred to as the viscoelastic spectrum. So viscoelastic materials are, classified according to the behavior, and you can have viscoelastic solid, elastic gel, and viscoelastic lipid. And these are defined by, their behavior at rest, as it were. So you'll see that over time, the elastic gel does not change with increasing frequency. The viscoelastic solid, the excuse me, the viscoelastic liquid again shows that the phase angle goes from close to 90 degrees. The viscoelastic solid, the phase angle trends towards 0. Right. So again, more solid-like phase angle towards 0, less than 45 degrees. More liquid-like phase angle towards 90, greater than 45 degrees. Right. So you.
Sorry, I have a question.
Sure.
What do you mean frequency in the graph?
Pardon me?
Frequency.
I didn't. Can you?
In the before yeah. What do you mean with frequency?
Sorry about that. What was your question?
Yeah. What do you mean when you say frequency in the graph?
Okay.
Hear that.
Yeah. All right. So typically, there are two types of tests that typically when you get a sample, you do what's called an amplitude sweep. So you apply a strain or a stress to see at what point the sample breaks, and you want to do any tests prior to that, because you want to do a test in what we refer to as the linear viscoelastic region. And I'm leaving out a lot of this information here because of time. So and eventually, then what you want to do is you want to do a test across a range of frequencies to see how the sample behaves when when the stress is applied at different frequencies. All right. So you will find then that sorry, as you go towards being solid, so we go from high frequency here. We typically do the frequency test in reverse. So you go from high frequency to low frequency. You'll see that the trying to get my mouse here to work. That the phase angle, sorry, will decrease as you get closer to the sample being at rest. So the sample is definitely more solid. All right, and you see that in the case of the viscoelastic liquid, in this case, then the phase angle tends to increase as you get towards 0 frequency, or the sample is at rest. So this is a far more liquid sample than this, or this for that matter. Does that make sense?
Yes, thanks, Eric.
Okay, sure. Again, I'm leaving out quite a bit of information here because in the interest of time, it's a bit difficult to cram everything together here. What material properties can we get from rheology? There again, it depends on what industry you look at, because different industries will look at different measurements, will need different information and so on. But generally speaking, we can find things like yield point, of course, viscosity. We can use the rheology to get information on the shelf life stability. We can look at temperature effects, freeze thaw. Okay, if you're a product that is subjected to freezing conditions, what happens? How does it change when you get back to room temperature? Gelation time, a product that gels, different modulus, relaxation time, and so on and so forth. You can even get a lot of information that you can get from a DSC. There's some information that you can get a lot of that information from a rheometer as well, as pretty much similar to what you get from a DSC with a this glass transfer TG or melt temperatures and so on. And here's just some a quick few examples of some applications that you might see in just about in literature or in a rheology book. This is an example of a nasal spray with different levels of cellulose, and you can see that there is a great deal of shear dependence with the higher level of cellulose. So the viscosity decreases as the stress level increase. In this case, we are measuring stress. At very low levels, it's almost Newtonian, so the viscosity doesn't change. Right? These are very small, small units here. We can also get some information again. So looking at the viscoelastic dispersion analysis of a dispersion here, this is a case where we're looking at different levels of polysorbate. And you can see that the higher level, it's about 2.5% weight by volume. As you, okay, yeah, the higher level tends towards, what scale is this on here? Let's see again. Right. Yeah. So okay. So yeah, the three different levels of polysorbate. One is doesn't react much to different frequencies. The higher level, as you decrease the frequency, the phase angle lowers, so it gets more solid. And the lower level, as you increase the frequency, it gets more liquid. So again, you can see the difference in how dispersions can be characterized using the rheometer in this case. Here's an example of a gel showing gelation properties where it increases the viscosity, or the modulus increases as the sample undergoes a gelation effect due to temperature. So this is a case where the temperature is programmed as a function over a certain time, and you can see the sample modulus increasing as it gets to a gelation point. You can also use the oscillation test to look at the potential stability of a product. You can see in this case where the two samples sits together here, and the phase angle is much higher, so the sample is more liquid. All right. In this case, you can see the difference in these are not the not the best pictures here, but it shows how you can differentiate the potential for sedimentation based on using the oscillation test. Typically, the higher the viscoelastic, the higher the modulus is, the more likely that the sample is going to resist sedimentation. Just here's another basic example, hyaluronic acid. You might be familiar with hyaluronic acid. This is used in a number of medicinal applications or treatment. It could be for ophthalmic or orthopedic. But the point here is that the material, the product is used has to be at different viscosities depending on the application. So for an ophthalmic product, the viscosity at a very low shear should be, 200,000 millipascal second. Whereas for a joint disease, we want a much lower viscosity, I guess, to facilitate movement, in the joints. Whereas with the ophthalmic product, you might want to have a higher viscosity product that will stay longer, so they can benefit before it drains off, whether through tears or just basically blinking the eye.
Eric, I have another question.
Sure.
If I want to increase the resolution time for our surface, I don't know what was the high shear? I am working with a viscoelastic liquid. What parameter do I have to consider for this?
Okay, so if you have a viscoelastic liquid and you really want to do a thorough analysis, let's say, you first start with doing an amplitude sweep or an amplitude test at a fixed frequency. All right, and you want to see whether the G prime or the G double prime, G prime, of course, the elastic component, or the G double prime, the viscous component. You typically want to see the G prime, especially, where that stays constant before it starts to break down. All right, and that's going to give you the zone through which you can do further tests. So the next test you would do would be a frequency sweep, let's say, to see how the sample behaves, when different when it's being different frequencies are applied to it. So you could tell then when the sample changes from being mostly elastic to mostly liquid, or from mostly liquid to mostly elastic, based on the frequency range that you're testing the sample at. I can discuss this with you afterwards if you because there are some other slides I can show you as well.
Okay.
All right.
All right. Thanks.
Thank you. Okay, so one other parameter that you can also measure is the yield stress, and this gives you an idea of the forces that are required before the sample starts to flow. And again, you could see in very practical terms where this would have some pretty good implications. Right, now, in terms of rheometers in pharmaceutical, if you're familiar with USP 912 is one that specifies the types of rheometer for measuring the rheological properties of Newtonian and non-Newtonian liquids and soft solids. And these can be used, of course, from formulation to product use, as you saw earlier. And these are basically it's a rotational rheometer with a cup and bob system, or cone and plate system, or parallel plate system. And there's also a European equivalent that specifies the devices that can be used. So what I'm going to do next is just basically show you some examples of how the rheology is used in the characterization of formulation, some formulation examples, and active pharmaceutical ingredients and the excipient examples. These can be large or small molecules. That's what we're going to look at, the next few slides. Right, so solubility or, dissolution time, of course, you put your sample in solution, chances are, the viscosity may increase or decrease. Suspension stability. Of course, nasal spray, ophthalmic treatments, injectability. The topicals, are becoming increasingly important. And tablet coating. And hydrogels, again, are getting increasingly popular for, the delayed release, of APIs as being used as a vehicle, to control the release of the drug. So the injectable drugs, if you look at, this gives you an idea of how important protein viscosity has become. There's a tremendous amount of, bioformulation studies increased over the last couple of decades. And this is just sort of an illustration of the amount of publications that you could get from Google Scholar if you were to use the words protein viscosity. There's a tremendous amount of increase because, again, people are starting to recognize, the importance of, protein viscosity or viscoelastic properties. Definitely want to try to better understand the viscoelastic properties because, the research has shown how, this can be better formulated or how you can get, more different types of proteins, different sizes and so on, can be used and how that impacts, the end products. So let's look at one example here is the monoclonal antibodies. All right, these are typically formulated to be administered in large doses and are typically highly concentrated liquid. And again, the viscosity might need to be varied as as depending on where it's being used. So for subcutaneous, you'd want a viscosity less than or around say 10 centipoise, 10 millipascal. For IV, you probably would want a higher viscosity, say 20 centipoise. And again, something like a viscometer, a basic viscometer, wouldn't be able to give you the sort of exact, accuracy that you would need for these extremely expensive, formulations. Just a minute. Let me. Yeah, sorry about that. Right. So, injectable drugs, the charge heterogeneity and whether or not they are, dipoles will certainly impact the viscosity of the concentrated solutions. And, various studies have shown that if the molecule has a dipole, which of course is, say an equal and opposite charge that's separated by some distance. and these are, could be impacted by protein composition or pH. If the distance becomes small, you develop this sort of a macro structure, which where the viscosity can increase dramatically. And just try to, pardon me here, my slide won't move. Okay, there you go. Right, yeah, so if the molecule has a dipole, the viscosity, the concentration will increase dramatically. So you could go from a much lower viscosity to an extremely higher viscosity, depending on, the, the protein composition and, the pH of your formulation. So this is something that, absolutely needs to be well aware of. And again, there are some proprietary data that I wasn't able to get a hold of, but again, just the idea that, you can have a pretty rapid increase in viscosity, in a relatively short period of time with the same formulation is something to consider. Here's an example of some monoclonal antibodies formulation being tested. And one of the beauty about the rotational rheometer is that you can test very small samples. You can test, samples down to about less than 50 microliters. And in this case, we're looking at a formulation with, a buffer at different levels. And you'll see that the smaller percentage of buffer applied shows almost a Newtonian type behavior here. We're looking at, say, at 234 milligrams per mil, a viscosity of about 15 centipoise. And, that's very low. But again, the idea is that the rheometer is able to distinguish at even these low viscosities, the difference in, the formulations. So between 100 milligrams and, 234 milligrams of a buffer, the viscosity and, the per buffer itself, the rheometer is able to very clearly distinguish this using very small sample size. And certainly this is not something you could get on a viscometer. Here's another example of an injectable drug where the viscosity, can sometimes change through binding. And in this case, it's a calcium binding protein, calmodulin. And what's important is that the portions of the apo and the holo, the apo being a part of the protein that consists of amino acids only. The holo refers to the entire protein, but they show a decrease in size upon binding to calcium. And you can see, the calcium balls here. So it goes from this to this. Have this tight helix, and the entire thing basically changes. So yeah, in this case, we're the binding of calcium is causing a change in viscosity because the molecule basically there's a decrease in the entire in the molecule overall. We're still on injectable drugs. In this case, it's conformational change, where excuse me, where the again, similar to what we looked at before, the addition of the calcium causes a significant change in the certain parameters, specifically the hydrodynamic radius of going from apo to holo, and also the intrinsic viscosity shows a dramatic decrease. All right, in this case. The viscosity is measured using what's referred to as solution viscosity, or would be a glass viscometer, and that also has a place, in R&D, but again, it doesn't have the. You can use a very small sample size to make this measurement, and from that you can also get some information on the hydrodynamic radius, which you might not be able to get specifically from the rheometer. Okay, biotherapeutic characterization. And this is looking at small volumes of injectable drugs that are extremely low viscosity, water-like. And what you want to do here in this case is look at the shear rate profiling. Again, profiling a range of shear rates from storage to delivery, let's say. You also want to do some temperature studies. Excuse me, the Kinexus rheometer really allows you to do that. Very small volume, 50 microliters. In this case, we were looking at measuring at a constant shear rate. And again, you can see how deadly accurate this is. Looking at mean value here of water. It's a standard oil. Again, this is just a tremendous amount of accuracy that you can get using very small sample size, which makes it certainly ideal for work in the pharmaceutical areas. And as the benefit of this also is that in this case, it might be an extremely expensive IPA that you're working with. You might want to use the same sample for to make other types of measurements, because we're talking about over time. The viscosity appears to be constant, so you would think that the sample has not undergone any kind of significant denaturation. So it might be able to use the sample for some further testing after this. So we've talked about using viscometry in looking at some of those pharma applications, and let's just take a quick look at using the oscillatory type test to monitor protein aggregation. In this case, the example here is bovine serum albumin, and in this case, the measurement was made at started at 25 degrees, heated up to 55, from 25 to 55, and held here for 5 minutes, and cycled a couple of times. Again, using a fairly small sample size, 100 microliters. And you can see then from that, the sample that's been cycled quite a lot here, and we're looking at the complex viscosity as a function of frequency, has undergone. The sample has undergone significant changes from start to cycling. All right. The viscosity has decreased tremendously. So after several cycles, you can see quite a difference. Cycle 1, cycle 2, and same thing here if you look at the elasticity. Okay, the viscosity, will increase. They both increase with thermal cycling. So you can see here that the viscosity, for example, increased from it says 3.3 centipoise to 7.37 centipoise. So tremendous increase in viscosity. Also increase in elasticity. If you look at the graph down here. So again, this goes to show that the temperature effects can be significant if the sample is again exposed to a range of temperatures over different time periods. The other thing that we can where the rheometer can be used is to mimic storage and transportation effects, and you want to know if how stable the protein is going to be after being subjected to the temperature, very low temperature, to maintain their stability. The idea is that they're going to be stable even at these very low temperatures, and of course it's a very expensive operation to, if you recall with the vaccines, some of them had to be stored at very low temperatures, and a lot of places just simply can't afford to do that. So so of course, one thing you want to do is to use rheology to investigate the freezing behavior of these protein solution. And as I pointed earlier, the glass transition temperature, is sort of a mechanical signature that can be used to look at, just how the material is going to behave across a wide range of temperatures. And it can also measure different effects from a DSC. So getting the information from the rheometer can be just as useful or even more useful in some cases. Here's an example of the effect of the concentration of sucrose, and you can see sucrose, solution in water, different levels of sucrose, and of course the whole freezing and cycle is disrupted here. As you go down in temperature, the viscosity modulus increase, as you would expect. But you can see there are two transitional points here in the higher level of sucrose. And this certainly will impact the dispersion. It's going to impact the crystallization, possibly phase separation. So these are important bits of information that you can get again from the rheometer by programming or testing your sample. It could be from ambient or from ambient, which is end use, to storage conditions, which is certainly well beyond minus 35 degrees. And you can see here that there's less an effect at the low levels of sucrose. Simply, sample simply increasing modulus stays frozen for the most part. But with a higher level, there is some transitional change that has to be completely deciphered and seen as to how it's going to impact the crystallization or the phase separation. Oops. Here's another example. Again, during freezing, these are again, antibodies, formulated with a buffer, and you can see again, the impact of changes based on the concentration. The impact of temperature changes based on the concentration. Here you're looking at the phase angle changes as a function of concentration. The phase angle changes, which basically tells you, it becomes more liquid-like, which sample becomes more solid-like, at different temperatures based on the concentration. You can see, for example, at 70 milligrams per mil, the sample becomes more solid-like at a lower temperature. Sorry, at a higher temperature than at 20 milligrams per mil. So again, this is information that that's really critical to development of these antibodies and how they're going to perform under storage conditions after being subjected to storage conditions. Let's have a quick look at nasal spray. And in this case, you need a really good balance between having the viscosity high enough so it stays where it's applied, and low enough where it's effective. It might for example cover a large tissue area and becomes more effective. So you're looking at balancing a balancing of the properties from when it's applied to the administration, the use of the product. And the FDA offers some guidance to this. That I'm showing here. Nasal spray formulation containing an agent which contributes to the viscosity of formulation should be tested and controlled at release and on stability with appropriate procedure and acceptance criteria. So we've seen this before, where we're making a measurement here on nasal spray with different viscosity thickeners. CMC is a carboxyl methylcellulose, which is a pretty popular thickener. This also has some use in the food industry. In this case, we are testing with cone and plates, pretty large size cone because of the low viscosity. And you can also see the test is being done over a very wide range of stresses or equivalent of shear. And what you're seeing then is that the higher level of CMC the degree of bioavailability and bioequivalence at different levels, you can see how significant the change might be. So something like this, for example, at such a low viscosity wouldn't probably be a good candidate, because it would simply, it just wouldn't apply very well, and you wouldn't get the benefit of this. So in this case, the fact that you can go from a very high viscosity to a very low viscosity, so a very sharp drop in viscosity, would make this, I'd say, a better candidate in that you can apply it, and once applied, the viscosity will lower significantly so that you can get the benefit from this. It will, will be a greater bioequivalency, if you like. So, of course, the viscosity of nasal spray need to be tested. Again, an edict from the FDA. But there are other factors that influence in nasal spray, and keep in mind that droplet size is a crucial component of all these sprays. So the viscosity is somewhat dependent on the droplet size. And, the higher the viscosity, the larger the droplet size is going to be for, for a given pressure. As you get lower in, in viscosity, you can see that the droplet size, decreases. We're looking at droplet diameter against spray pressure. So again, that also has to be considered when formulating, these sprays. Keep in mind also that there's some viscoelastic influence in viscoelastic influence in this as well on the atomization of the solutions. For a material that's Newtonian, which probably wouldn't be a good candidate, of course, for a droplet spray. For the breakup is controlled by the viscosity and the density, and this is what you see. Some nice work done by some folks at the Carnegie Mellon University, comparing a Newtonian fluid breakup to a viscoelastic fluid, and the components that are important for viscoelasticity are the length of the jet diameter, and interfacial breakup. So you can see that in formulating a spray, you will need, again, some amount of viscoelastic properties, to control the spray. In the case of a Newtonian fluid, pretty much would be lost immediately. So there has to be some, elastic properties to the spray that's been developed, where again you can apply it at a higher viscosity, and the elastic properties will keep it as it's been applied intact for some period of time before the viscosity decrease over time, and the user gets the benefit of it. So the other thing would be eye drops. Again, similar to sprays, there's a balance that needs to be found where you simply do not lose the drug as you drop it in your eye. All right. It's been shown that most use of eye drops suffer from really low availability, certainly less than 10%. So what you apply, the active ingredients, you definitely will get less than 10% of the active ingredients as a result of drainage. It gets diluted by tears and your own blinking action. So with the eye drops, then let's say look at the viscosity compared to water. All right, you want to start out with something that's significantly more viscous than water. So in say at least 6 times, 7 times the viscosity of water, and this is what's commonly used, or was commonly used in the industry. Something several times more viscous than water, but you really wouldn't get the benefit, because all would be lost after you've applied, or after you've drops. It rolls off your eyes, and you get less than 10% of this. What might be a better idea is to use a gel, which has the advantage of, it's far more convenient. It stays where it's applied, and over time, the user can get the benefit of this. So let's say, for example, in this case, we're looking at viscoelastic properties of a gel, and we're looking at, let's look specifically at G prime, which is the elastic component, G double prime, which is the viscous component. So it starts out being when it's applied, it starts as being more viscous. So it's more liquid-like. So you can actually, get it into your eye. And over time, it hardens up. So you apply it and it stays in place by the fact that it becomes more elastic or more solid-like. And over time, eventually, over time, the drug disperses and you get the full benefit of it. So it has a much longer residence time and you're able to get, the full impact of the active ingredient. Here's another example of gel formation. And in this case, this is an example of, a test that could be done. And again, we're looking at modulus or moduli over time. So again, we start out with a more liquid-like material, right? Where G double prime is higher, so it's more liquid-like. And it's applied, and then there's a crossover point when it becomes more elastic, more solid-like, all right? So this is a test that could be used to essentially move along the point where it becomes more solid-like. So you can basically design a gel, using this test, because it shows you where over what time it becomes more liquid. It starts out more liquid-like, and eventually it becomes more solid-like. So you apply it and it stays, right? A longer residence time. And over here would be sort of an illustration of, I apply a drop, and do I want it to stay as a drop, or do I want it to be fully dispersed over time? So the decision of how you'd like the product to end up can be controlled by doing this test. Right, there you go. An example of, in this case, it's a thermally setting drug, and we're looking at the efficacy of the eye drops. About whether how long the gel formation takes place or the strength of the gel. In this case, this is an experiment that done with the eye drops in artificial tear and without artificial tear. And you can see, excuse me, that with the artificial tear, it takes a longer time for the gel to set. All right. You can just look at the square versus the triangle in red, which is the elastic modulus or the storage modulus. This very quickly sets up where there's no artificial tearing involved. It takes a longer time with artificial tear. So again, the efficacy of the eye drops really is a function of the time to gelation and the strength of the gel itself when it's formed. So you can, in this case, where there's no tear, as it were, which is certainly not practical, it sets up quicker and it's also higher in strength, which can be a good thing. So as I said earlier, when dilated with artificial tear, the time to set up is much longer. So you would need, of course, some kind of happy medium between these two. This sets up pretty quickly. I'm not quite sure if that's what you really want. Finally, creams and ointments. And again, the FDA has guidelines for this, and how they should be assessed. There's a lot of medicinal being applied in topical form these days. And what's important is the things like the appearance and the particle size and so on. And of course, we want to monitor the flow behavior of semi-solid dosage forms. And these are the type of tests that they recommend that you perform: complete flow curve, viscosity curve, a yield stress, and basically this determines how much force is required to dispense the product. And we want to see also a viscoelastic response. And this is going to give us some information about the storage of the product and whether or not it's going to separate and how stable it is. And here's an example of a viscosity shear rate curve of 4 topical creams. So 3 generic ointments compared to a control system. And again, the trend is very similar, but you can see how different. Oops, sorry. Yeah, the trends are similar, but you can see how different they are from the control. If that's what your goal is, to maintain a certain viscosity across a range of shear. In this case, what we used was a 25 millimeter plates with a 1 millimeter gap, and a shear rate from 0.01 up to 1,000 inverse second. But again, the whole point in this exercise is that if you have a product, a controlled product, works very well, then obviously your goal is to get a similar, if you want to create other products with similar performance characteristics, one of the parameters you want to look at is the viscosity. Exactly how the viscosity decrease changes with increasing shear and also with temperatures and so on. So this brings us to the end of this presentation. Thank you so much for attending. Hope you got some information out of this. I know it was a bit long and it's very difficult to do this remotely because I can never get the audience reaction and whether or not it's making sense or not. But feel free to contact me if you have any questions. I can be around for a while to answer any questions now, for that matter, and or any comments. Again, thanks much, and I'll turn it over to you, Jesus.
Our thanks, Dr. Alex. Before all, I want you, excuse me, there are a lot of time that I'm not speaking. But I want to congratulations for the conference. At the beginning, you asked if somebody went in this or in Reology. So I remember in 1995, I worked in pharmaceutical situations to work analyzing some substance to increase the viscosity. So and now I'm interested to work in some semi-solid industry. So I try to do some process in semi-solid. So about your your experience, what kind of equipment do you suggest me to use? I'm trying to do some ointment and grades and gels. So I'm interested that you suggest me some equipment that about your experience. You understand?
You listen, Eric?
Sorry.
Oh. Si quieres, puedo repetir.
Sorry, I'm interested to do some or to produce some semi-solid products. So, about your experience, why or what of those equipment that you mentioned in your conference do you suggest me to use? Well, remember I'm stopped. I'm interested to do that.
Hello, Eric?
Hello?
Can you hear us?
Yeah, I can hear you. I can hear you. Can you hear me now?
Yes.
Okay, good. No, I was saying in response to the question, you mentioned semi-solid materials, and you would typically use a parallel plate system. Typically, depending on the modulus of the sample, you could say use a 20 millimeter or 25 millimeter diameter plate system, or if it's a sample that's likely to slip, you might need to use a plate system that has either serrated or roughened, maybe sandblasted surface to make sure that the plates make proper contact with the sample, and the sample is not slipping between the plates while the test is in progress. So with something like that, then you should get pretty good results if you for doing viscoelastic testing, and also for doing some amount of viscometry testing, keeping in mind that for some samples, like a semi-solid, soft solid, you might not be able to get up to very high shear rates with the rotational rheometer because of the edge effects, and the samples might, when you get to high speeds, high rotational speeds, the sample might through centrifugal force just spin out from between the plates. So so that you need to be aware of, but you should be able to get very good viscoelastic properties, and you can get yield stress. You can get some amount of viscosity testing up to a reasonable shear rate, but maybe not to very, very high shear rates. Hope that answers your question.
Well, I'm interested to do some semi-solid, where in this case, semi-solid.
Yeah.
Semi-solid, where I'm trying to do some health on the other grades. So I asked you this because I never worked in this case, rheology of grades. I told you before that I was working in some pharmaceutical suspensions and to analyze some something to increase viscosity, sodium alginato, cellulose, or another something like that. So, but I never worked in semi-solid. I'm interested to know what kind of equipment can I use, or do you recommend me to work? Because I'm interested to do some startup relation with this oil direct to produce that kind of pharmaceutical products. That's why I'm a pharmaceutical. I'm a pharmacist. I'm a professor of the UDA, well, the University of Guadalajara here. I'm Cuban, but I'm trying to do something in Mexico relation with this kind of products. I'm interested. I come to this conference because I knew that you will work about, well, you will talk about this kind of important technique to rheology, and that's why coming to know something like that. Well, I told you before that, excuse me, my English, I am not you.
I think I understand you, and but yeah, what I
want to know about equipment. What kind of equipment they are suggesting to analyze, or all of that, all of those equipment that you mentioned,
Mhm.
can I use to analyze grains, for example?
to analyze what? Sorry.
I think equipment. So, and if you want me to jump here.
I did not get the
Okay. So, for equipment, in good application, which is like handling over we like a spread on the thread, something like that. The rotational geometry